Hello, I'm Nona Carvalho, and today I will be going over my answers and worked out solutions to the 2012 AP Physics C Electricity and Magnetism multiple choice exam. This is the 2012 publicly released exam, which means Collegeboard actually put it online and it's open to anyone to look at and try it themselves. So you can find the multiple choice questions, FRQs, answers, everything online, as well as the scoring statistics, and you can see how many points you would have gotten and whether that'd be a 5, a 4, or a 3, and so on. So take a look at that as well. This will probably be my last video on before the exam, but I might make another one for the 2008 practice exam that I found. But other than that, I wish you best of luck on the exam tomorrow if you're taking it. And if you enjoyed the video, if you find it helpful, please leave a like and subscribe for more. Starting with number one, we're told that a proton moving along the positive x-axis enters an electric field that is directed along the positive y-axis. What is the direction of the electric force acting on the proton after it enters the electric field? Well, really the movement of the proton itself does not matter because we're talking about an electric field. It's just there to trick you into thinking that it's maybe a magnetic field that you have to be thinking about. So if it's a proton will move in the same direction as the electric field. Well, it will feel a force in the same direction, that is, which means that the electric force is also going up, and so the electric force that acts on it is also in the positive y-axis, and so it's D. Number two, we're given here a charge distribution shown above, and we're asked the net force on the particle with charge plus q due to the other two charges is in the plane of the page and directed towards. And well, let's think about what each charge is causing in terms of the electric field on this point right here. So this charge here will be repelling, right? We'll have a electric field that's moving away from it, and then this charge right here will have one of equal magnitude, but it will be going towards the negative charge. And it's, by the way, equal magnitude because same charge magnitude and also the same distance away. And so that means that the y components of these electric fields will cancel, and all that you'll be left with is a horizontal component that's going directly to the right, and so the answer here is C. Number three, we're still working with the same charge distribution from before, but now we're being asked about the magnitude of the force on the particle plus q because of the other two charges. So we sort of need to use the same information from the previous question. But keep in mind, the electric force is given by this equation. This is on your answer sheet or formula sheet. And uh, from the previous question, we know that only the x component here of the electric field actually doesn't cancel because of the two charges. So we need to really just be thinking about what's the electric field in the x direction because of each charge. And so I'm thinking about this charge right here. It will be given by this formula right here, right? And r is going to be a in this scenario. But then we want to multiply it by cosine of theta because that will give us the x component, right? So if this is theta here, which by the way is going to be 60, then taking the cosine of that will give us the x component. And so then that means that the total electric charge will be actually twice that because this charge right here will have the exact same electric field in the x component as well. So what we'd be left with here is something that looks something like this. And then keep in mind, we are then going to multiply this by q because we actually want the force. And so let me sneak a q in there. And then what you'll get is that the answer is E. Number four is still dealing with the same charge distribution, but now instead of electric fields or forces, we're now asked about potential energy. And so if you look at your formula sheet, the formula for the potential of a point charge is going to be given by this right here. And that's what we have here is point charges. And so at this point Q, we can just sum both of them. And so we'd be left with something that maybe will look like this. And so keep in mind, since they have the same distance to the point Q, and they also have the same magnitude of charge, but they are opposite, this will basically equal 0. So there's actually a potential energy of 0 at point where the plus Q is. Number 5, all the following statements about an isolated solid charged conductor are correct, except, well, let's draw what a conductor that is solid would look like. And let's just imagine it has a positive charge. It would maybe look something like this here. And so all the charges will be collecting up on the outer surface. This should be a familiar image to you. The electric field inside is going to be 0. And again, that's because it's a conductor. Charges are free to move around freely, and so they're going to try to get away from each other as much as possible. And so that's why they collect up on the surface. Also, the voltages will be the same all throughout inside of here because the electric field is 0. right? And so since voltage is just the integral of E, well then if that's 0 right there, then your voltage will not be changing. So now going through this, we've actually already answered a lot of these. A, all parts of the conductor are at the same potential. That's true, so it's not the answer. B, all excess charges reside on the outer surface. That's also true, so it's not the answer. C, the net charge enclosed by any surface lying entirely within the conductor must equal 0. That's also going to be true, and the reason for that is because of Gauss's law. If you were to draw a Gaussian surface inside of here, and it had a net charge, then that means it would have an electric field, and so it would break our rule about electric fields being 0. D, the electric field just outside the conductor is directed parallel to the surface. No, so the answer here is going to be D because that's wrong. It's not going to be parallel, it's going to be perpendicular. That's something that you should know, is that the electric field is always going to be perpendicular to the surface of a conductor, like so. But let's also just go through E. The electric field intensity inside of the conductor is 0. That's true. That's actually probably the most important fact you need to know about conductors. And so it's not the answer. D is the answer. Number 6, we're told that two long straight parallel wires are held fixed as shown above, and a voltage is applied to wire X, creating a current I sub X to the right. And the wire experiences a magnetic force of magnitude FB toward wire Y, so it's feeling a force in that direction. And we're told, assuming the resistance of wire X is constant, which of the following graphs correctly illustrates the magnitude of the magnetic force F on wire X, a function of the voltage V applied to the wire? All you have to do here really is combine two different equations, both of which are in your formula sheet. The first is that the magnetic force felt by a wire in the presence of a magnetic field is going to be given by this formula right here. And it looks a little bit more complicated than it actually is because this usually just simplifies to be this right here, where L is the length and I is the current. Then all you have to know is that the current of a wire is going to be given by the voltage divided by R, and since we're told that the voltage here is going to be constant because it's applied like that, and also the resistance is constant, we can just plug this in and say that FB is going to be given by VLB over R. And so as you can see here, FB is going to be directly proportional to just V, and so the only answer here that seems to be consistent with that is going to be D because it's a straight line pointing up. And so that's our answer. Number 7, we're still dealing with the same setup from before, but now we're asked about 3 following statements. And I would recommend you sort of just memorize these facts here instead of trying to derive this on the test because it could be kind of a time waster. But let's go through each one. 1, it carries a current in the same direction as current X. That's saying that Y here is going to be carrying current like so, and this will be true. And why is that? Because we're told that wire X feels a force that's attractive to wire Y, and you should just memorize that when wires are parallel, if they are in the same direction, the currents, then they will have an attractive force to each other, and if they are in opposite direction, they'll be repelling. So 1 is true. The number 2 is it experiences a force directed away from wire X. Well, that would tell us that it'd be going like this, which you can again figure out by using the calculations of a magnetic field and the force on a wire using the right-hand rule, that this just cannot be true because they will feel either a attractive force to each other or a repelling force, but not sort of a force that's in the same direction for both, if that makes sense. So 2 cannot be correct. And then 3, it experiences a force of different magnitude than the force on wire X. This is also not true. You can derive it as well, but this will never be true for this type of system here. And also you can sort of think about the Newton's third law that you'll have a force of equal and opposite direction. And so by that, I can say that only statement 1, which is B, is going to be correct. Number 8 is still with the same setup from before, but we're told that if the distance between the two wires is tripled, what is the magnitude of the new magnetic force exerted on wire X? Well, let's come up with a formula for the magnetic force. This will be given on your formula sheet, and it will look something like this, and we've shown this already before. And simplified, this will just become this. But then we also don't know what the magnetic field itself is, and this is not given to you on your formula sheet, but you can derive it using Ampere's law. But it will look something like this, where R here is the distance between the two wires. And so, and by the way, these are technically different magnitudes here. So putting this all together, that tells me that the formula for the magnetic force felt by or exerted on wire X is going to be given by this here. Hopefully I wrote that correctly, but what you'll see is that if we were to triple the radius, like so, we'd be cutting the magnetic force from before by 3, and so the correct answer here is going to be B. Number 9, we're told that a proton moving to the right at a constant speed v enters a region containing a uniform magnetic and electric fields and continues to move in a straight line. The magnetic field B is directed toward the top of the page as shown above. The direction of the electric field must be, well, the key word here being that it continues moving in a straight line, which is to say it's not feeling any acceleration and therefore force in the up or down direction. And so if we have here our proton moving with this velocity to the right, and it has a field B that's going up like so, what will be the force that it experiences? Well, you can use here the right-hand rule, and what you'll get is that the force is, actually it's a little bit difficult to draw here, but it'll be feeling a magnetic force that's going out of the page with the way that it's moving. And so that must mean that its electric force must be in the opposite direction and of equal magnitude. And so if the electric force is going into the page, because it's a proton, that must mean that the electric field must be also going into the page because a proton will just go into the same direction. And so the correct answer here is going to be A. Number 10, we're shown here three different capacitors with different areas and distances between the plates, and we're told, suppose all three capacitors have a charge of plus Q on the top plate and a charge of negative Q on the bottom plate. Which of the following is true of the potential difference across the plates of the three capacitors? So we want to be thinking about the voltage here, which is going to be given by this formula for capacitors, and this is in your formula sheet. And we are told that the Q stays the same. Okay, so this stays the same, and so what might be changing here is going to be the C. And so the capacitance is going to also be given by this formula here from your formula sheet. And this actually determines the capacitance based on the physical properties of the capacitor. And so plugging this now into our formula, we get a new formula here, which is going to be looking like this here. And so now we can think about how the voltages will differ based on the different properties of these capacitors. Okay, so it seems like to get the biggest voltage, it would be having a big distance and a smaller area. And so to me, that seems like 2 is matching that, right? So to increase the voltage, you would increase the distance and also decrease the area if possible. And capacitor 2 has the biggest distance and also has a pretty small area compared to the other ones. And so the one that has the biggest voltage is 2. The answer is B. Number 11, we're still working with the same capacitors from before, but now we're told that they are connected in parallel with a 9-volt battery. Which of the following is true of the electric field between the plates? And so this can be a tricky question if you're still thinking with the same mindset of the previous question where the voltage did change, but now keep in mind it's connected to a 9-volt battery and they're in parallel, which means that the voltage across each capacitor will be staying the same. So how are we going to connect the electric field of this? Well, it's actually pretty simple. We can just use this formula here from our formula sheet. And because capacitors have constant electric fields inside of them, we can just simplify this to be something that maybe just looks like this right here. And we just care really about the electric field magnitude here. So whatever has the biggest distance here will have the smallest electric field, which is to say, looking at this, it already seems like we can say 2 is going to be, or going to have the least amount of electric field because it has the biggest distance. But also we can confirm that 1 and 3 will have the same electric field magnitude because their distances are the same. Number 12, we're told that the electric potential along an x-axis is given by the expression V is equal to ax minus bx squared, where a and b are constants. At what point on the x-axis is the electric field 0? Really, this is just a very simple calculus problem, like a first semester calculus problem. But all you need to remember is that the electric field is going to be given by this formula here. And so if voltage here is going to be ax minus bx squared, taking the derivative of voltage is going to give us just a minus 2bx, and then we just set this equal to 0, and it doesn't really matter that we have the negative there because we're setting it equal to 0, and what you'll get is maybe something that looks like this, and then finally we can get this answer here, a over 2b, so the correct answer is B. Number 13, we're told that a uniform magnetic field B of magnitude 1.2 teslas passes through a rectangular loop of wire which measures 0.1 meters by 0.2 meters. The field is oriented 30 degrees with respect to the plane of the loop. As shown above, what is the magnetic flux through the loop? Well, all we need is the formula for magnetic flux, which is going to be given by this. And I would recommend memorizing that it's an integral with a dot product inside and not just B times A, because this is where this comes in handy. Well, what we need to know is that the dot product here is talking about the dot product between the vector that creates the normal of the loop here and the vector of the magnetic field, like so, which means that actually their distance or their angle between them is going to be 60 degrees, not the 30 degrees that they give in this question. So that might be there to trick you. So we can rewrite this as b cosine 60 degrees d times dA. And because the magnetic field here is constant, they tell us, we can then just say that the magnetic flux is going to be given by this. And when you plug in all the values for this, where A here is going to be 0.1 times 0.2, what you'll get is that the answer is B, 0.012 Teslas times meter squared. Number 14, we're told that a metal sphere with radius r1 has a total electric charge of magnitude q. An uncharged metal sphere with radius r2, where the radius of 1 is bigger than the radius of 2, is then connected by a wire to the first sphere as illustrated above. The separation of the spheres is much greater than the radius of either sphere. When equilibrium is reached, the spheres will have and this question can be very, very simple, very quick to get as long as you know what you're looking for here. And what I'd be looking for is that we have a metal sphere, right? And then we have another metal sphere. Both of those are conductors. They're connected by a wire, which can also conduct electricity, which is to say we basically just have a giant thing here that maybe looks like this, that's all conductors, and something you need to 100% memorize for the exam is that conductors have an electric field of 0 all of inside of it, and they also will have the same potential all in everywhere that's on the inside of the conductor, which is to say we can already just go straight to E, which is that they will have equal electric potentials. Number 15, we're still talking about conductors, but we're told that a negatively charged conductor attracts a second object. The second object could be which of the following? And so let's think about each of these objects. So let's imagine here we have a negatively charged conductor, and let's think about a conductor with a positive net charge. Here's a conductor with a positive net charge. Uh, and certainly this would be feeling an attraction to that, right? So 1 seems correct. Okay, 2, a conductor with 0 net charge. Well, we might think because it has a near 0 net charge, it wouldn't be feeling any attraction, but that's not true because it's a conductor, which means that the charges are free to move around. And so originally, maybe our conductor would look like this. There's no specific charge distribution, and it would look like that. But in reality, what would happen is that the protons, well, actually the electrons would feel a repulsion from the negatively charged conductor, and so they'd move here, and so then you'd have a net charge that's positive here and a net charge that's negative here inside of the conductor. And what would happen is that there would be a net attractive force, and that's because, again, the forces scale with the distance, and so since the positive charges are closer to the conductor than the negative charges are far away, there actually will be a net attractive force. Okay, so 2 is also correct. Now 3, an insulator with 0 net charge. Well, if the charges can't move around in an insulator, then surely this won't feel an attraction either. But the thing is, this a little bit of a trick question. It never specifies what the charge distribution is for this inductor. So it could be possible that it looks like this, and this still has a net charge of 0, but the charge is not spherically symmetric or anything. And so in the same reasoning for the inductor, or sorry, for the conductor from before, this would still feel a net uh, attractive force to the conductor. And so 1, 2, and 3 are all correct. The answer is E. Number 16, we're told that 3 resistors having resistances 3, 6, and 9 ohms respectively are connected in parallel with a 10-volt battery. So let me quickly just draw that out actually. Okay, and we'd have 3, 6, 9. Okay, true statements about the circuit include which of the following? Well, if they're in parallel, that means that the voltage across here will be the same. It will be 10 volts. And so, uh, actually by that we can already skip to 2 and say that that's going to be correct. But now let's think about number 1 here. The current in the 9 ohm resistor is 3 times the current in the 3 ohm resistor. No, it's actually going to be the opposite. And why is that? It's because of this formula here. If the voltages are staying the same, then if you were to triple the resistance, then you'd actually be cutting the current in thirds like so. And so number 1 is not correct. And then number 3, the power dissipated in the 9 ohm resistor is greater than the power dissipated in either of the other two resistors. Well, the formula for power is given by this, but let's turn this into this formula instead, which is just again using actually this right here. And the reason this is useful is because, again, the voltage will be the same for all three resistors, but the currents will differ. And with this, we can clearly see that, again, the 9 ohm resistor, by having the biggest amount of resistance, will actually have the least amount of power as well. So 3 is not correct, and so the only answer that's correct is number 2, which is B. When two resistors having resistances R1 and R2 are connected in parallel, the equivalent resistance of the combination is 10 ohms. Which of the following statements about the resistances is true? So we have here a R1 and R2, and we're saying that we can just express this as 10 ohms like so, and the formula that we use for that is going to be this right here from your formula sheet. And to be honest, I would recommend just sort of memorizing this fact, which is that whenever you add resistors that are in series, or sorry, in parallel, then the equivalent resistance will always be lower than any of the resistances in that parallel system. Uh, and then the opposite, if you're adding in series, the equivalent resistance will always be greater than every single resistance or resistor uh, within that series. So we can actually sort of just skip already here and say that it's going to be uh, A right here, because we know that the equivalent resistance, which is 10, must be less than R1 and R2. And you can try around and kind of mess around here with this formula here to determine or derive why that must be true. But yeah, it's going to be A. Number 18, two particles with a charge negative q are fixed at distance L apart as shown above. Each particle experiences a net electric force F. A particle with a charge plus q is now fixed midway between the original two particles. As a result, the net electric force experienced by each negatively charged particle is reduced to F divided by 2. The value of q must be. Well, first let's figure out what the original electric force must be before we place a charge right there. And it's going to be the same for either one, but let's just imagine for this one here. Well, it will be given by this formula here, if you remember, and we can plug in the values here. Since both of them are q, or negative q to be specific, it will be q squared up here, and this is just going to be L squared. Okay, so that's the original force. Then what we're told is that when we add a plus q charge in between, where this is now L divided by 2, that the net electric force felt by that same particle from before is now going to be F divided by 2. And so let's sort of think about what that would look like. Originally, there was this electric force here, F, and it was repelling away from here. But then when we add this charge plus Q, now suddenly that net force is only going to be half of what it was before, which means there must be a force that's in half of magnitude of F caused by plus Q. Okay, so that must mean that the charge here caused by the little q here is going to be F divided by 2, so same thing as here, and that is, by the way, the magnitude here. And so that must mean it's going to be k or k times q squared over 2l squared, like so. And so I just got this from taking this and dividing by 2, but keep in mind this will also be, we can just figure it out manually by using that same formula from before. Now we have q times k times little q, and then the new distance here is going to be L divided by 2 squared, which is to say it's going to be 1/4 of L squared. And now we can see we can solve for Q with here. There's going to be a lot of things here canceling out, but essentially you'll eventually get that little q must be equal to big Q divided by 8. And so the answer here is going to be D. Number 19, we're told that two objects on a horizontal frictionless surface each have a charge of plus q, and each are fixed in place on the x-axis in the same distance d from the origin as shown in the figure above. A particle of charge negative q constrained to move along the y-axis is released from rest. After release, the particle will, well, first let's think about the force that it will be experiencing. But first, also let's draw out the electric field. So this charge right here will cause an electric field in this direction. This one will cause one in equal magnitude and opposite, or I guess symmetric to the y-axis like so, which is to say that the net electric field will be like so. And because it is negatively charged, that must mean the force that it's feeling is going to be in the opposite direction. Okay, so we can already eliminate some answers here like A, C, um, D could still be correct, and E could also still be correct. So now we're left with something that says oscillatory motion. And if you're like me and you took mechanics last year, in the year that coronavirus hit, you didn't get to really learn about oscillation much. And so uh, on a normal day, I don't know if I'd be very confident about this answer, but I still kind of have an idea of what oscillations mean, which is to say that it's going to be going basically back and forth, back and forth, back and forth, like so. And if you think about it, this will indeed be true because originally it's having an acceleration that's going to be downward because of the force. But once it reaches this point, the acceleration is 0 now, and actually, as it continues going in this direction because it carries a velocity with it, the acceleration is going to be in the opposite direction. And so it will always be moving basically opposite of the direction of the acceleration that it is feeling. And so because of that, it's going to be oscillatory motion. If you really think about these other ones and you sort of do a thought experiment in your head, those don't make sense. B is the only one that makes sense here. Number 20, we're told that a uniform electric field E exists between the two large oppositely charged plates shown above. If the distance between the plates is increased without changing the charges on the plates, which of the following statements can be justified? And there's an easy way to do this, and there's kind of a harder way. The harder way would be to actually quickly do Gauss's law here by using a cylinder like so, and then what you'll basically get is that the electric field is given by this formula right here. And all this is to say is that the electric field does not depend on the distance between the plates, okay? Uh, it just depends on the surface charge density. So we can already say that A and B are incorrect, but then what about the potential difference? Well, potential is going to be given by this formula right here, right? And this is from your formula sheet. And so that's to say that if we were to increase D here, the distance between them, then surely we're going to be increasing the voltage as well. And so the answer here is going to be D. Number 21, we're told when two identical resistors are connected in series to a battery, the total power dissipated is P. When the same two resistors are connected in parallel to the same battery, the total power dissipated is, and what we need to be thinking about here is the equivalent resistance, right, of these setups. So when we have in series, and they're two identical, let's just say each one is R, then the equivalent resistance will just be 2R. Pretty simple. When they are in parallel, like so, the equivalent resistance will be given by 1 over R plus 1 over R, which simplifies to just be uh, R over 2. And by the way, that formula that I was giving is going to be for 1 over the equivalent resistance, so you just flip your final answer there. So that seems to me that we are increasing here the resistance by 4, or I guess in a way we're going to be uh, cutting it by 4 when we go from the series to the parallel. And now we need to connect this to the power. And so power is going to be given by this formula here from the sheet. And then if you use the fact that I is equal to V divided by R, you can get that power is going to be V squared over R. And so then you can see here that if you were to, when you're going from a series to a parallel system here, which is what's happening, then you'd be cutting this by 4, which means we're really just multiplying by 4. And so the power that's experienced by the ones in parallel is going to be 4 times as much as in series. Number 22, a positively charged particle in a uniform magnetic field is moving in a circular path of radius r perpendicular to the field. How much work does the magnetic force F do on the charge for half a revolution? Okay, so we have to work here with angles and stuff. No, we don't. Actually, it's just going to be E. And why is that? This is a fact that you should memorize for the exam, is that a magnetic force does not do any work on a charged particle. And why is that? Because think about it. If a charged particle is moving with this velocity here, it can only ever feel a magnetic force that's perpendicular to it, okay? And then if you think about it, that means that all the magnetic force can do is change the direction of the velocity, not change the magnitude. So the speed does not change. And then think about it. Work is going to can be thought of as the change in kinetic energy. Kinetic energy is given by 1/2 of ignore that 1/2 of mv squared, like so. And so if this here is not changing, keep in mind we're squaring, so the sign does not matter. If this is not changing, then this is not changing, which means this really here is just 0. Number 23, we're given a diagram of equipotential lines produced by charge distribution, and we're asked for which 2 points can a negatively charged particle be moved from rest at one point to rest at another point with no work being done by the electric field. So if the work is 0, keep in mind that the work can be also thought of as that's really the magnitude of change in the potential energy, and potential energy is given by this formula here from your formula sheet, which is the change in voltage. So if this is 0, then the change must be 0, which must mean that the change in voltage must be 0, given that we know that at least we have a net charge. So we really just want to see movement along the same equipotential line. It's in the name, equipotential, they have the same potential. And the only one here that matches the description is going to be A and C, which is to say the answer choice B, because we're along the same equipotential line of plus 2 volts. Number 24 is still the same equipotential diagram from before, but we're asked A positively charged particle is moved by an external force from rest at one point to rest at another. For which of the following motions would net positive work be required by the external force? Well, the way I like to think about it is that if we have an external force doing positive work, that must mean it's basically going to go against what would be naturally happening given the forces that are currently in the system, which is here we're going to be seeing electric forces. So naturally, a positive charge, right, would be going from a place of positive potential to a place of negative potential, right? Which is to say that really what's happening here is that we're moving a charge from negative potential to higher potential by our external force. So this here is external force, and that would produce a work that is positive, right? Because moving this to here is positive work, but that's for the electric field, or for the electric force, I should say, while the external force will be counteracting that. So what 2 points here are moving from a negative voltage to a higher voltage, or just increasing in voltage? And that's only going to be answer choice E here, which is saying we're going from D, which is negative 6 voltage, to B, which is going to be positive 6 voltage. Number 25 is still the same equipotential diagram from before, but now we're asked the electric potential shown in the diagram could be created by which of the following. And so before we look at the answers, because that could, kind of take a while to go through them, let's instead try to come up with it on our own. Uh, since these are equipotential lines, and we know that electric field lines are perpendicular to equipotential lines, and we also know that electric field lines go from positive to negative voltage, we can already sort of be drawing what these will look like. It'll probably look something like this, and I'm just going to imagine there's probably a charge there, and you'll see exactly why this works out. But as you can see here, all these lines that I'm drawing here are generally perpendicular to the equipotential lines, and they're also going to be going from positive to negative charge, like so, or positive to negative voltage. And so it would look something like this. And so now looking at our answers, uh, what the answer is actually going to be is D here, and you might be confused. Two long lines of charge. It seems like we really just have a point charge here. But keep in mind, and this is a sneaky part here, is that this is really just a cross section, which is to say that you can imagine basically a long line of charge that's going into the page, up here and down here as well, and we're just looking at a cross section of it. And you might be thinking, okay, why must it be a line of charge? Why couldn't it be E, for example, which is saying a similar thing, which is a long line of positive charge and a negative point charge? The reason it's not going to be that is because the voltage magnitudes are going to be the same, and so we'd imagine then that there must be an equal magnitude of positive charge up here at the top and down here at the bottom. So it can't be that. And also these other ones here cannot be, because we see both a positive and negative voltage in this diagram. And so that would imply that we'd be seeing both positive and negative charges in our distribution as well. Number 26, a magnetic field perpendicular to the plane of a wire loop is uniform in space but changes with time t in the region of the loop. If the induced EMF in the loop increases linearly with time t, then the magnitude of the magnetic field must be proportional to. Well, the key word here is that the EMF in the loop is increasing linearly with time t. Linearly, that means that we can say, actually, let's put it like this, that the EMF is directly proportional to t, and if you remember, the EMF is equal to the change in the magnetic flux with respect to time, and the magnetic flux is going to be approximately given here by BA. We can just quickly assume, and we're told here that the magnetic field is going to be changing. It changes with time t. So really, the EMF is going to be given by the change in the magnetic field magnitude here times A, and so keep in mind that we're taking the derivative, and so we can think about basically taking the integral of this to get the change in the magnetic field, which is to say that if this is true, then this must be true, that the magnetic field is going to be directly proportional to t squared. So the answer choice here is B. Number 27, we're told that a loop of wire carrying a steady current I is initially at rest perpendicular to a uniform magnetic field of magnitude B as shown above. The loop is then rotated about a diameter at a constant rate. The torque on the loop is maximum when the loop has rotated with respect to its initial position through an angle of, and sorry for speaking so fast, but this is like take number 7 here, because this is kind of a hard question to explain. But to explain it, I'm gonna try my best here, which is that imagine that we're looking at the field now from this direction, sort of in that direction, right? And we're going to be rotating the loop across that diameter. So initially we have here the magnetic field going in this direction. And initially the loop is like this. And here it's actually not feeling, it's not going to be feeling any net torque. But as we rotate, so let's say now we've rotated it like this, the magnetic field is here, okay? And the force that it will then be feeling is going to be like so, okay? And so this would be how you'd be calculating the torque. But torque is going to be given by this formula here. It's the cross product of F with R, where R is basically going to be the vector from the center or axis of revolution here. And so that's going to be this right here. And as you can see, let me try to use a different color here. The angle right there is kind of small so far. But we can imagine as we rotate this further, which is all the way to here, the torque will be at its maximum because the forces are going in these directions here. And you can again check with the right hand rule why this is true. And the r vector here from the axis of revolution is going to be uh, like so, which is to say that it will be having a 90-degree angle. And so because we're taking a cross product, that means we have to think about the cosine of the angle. And so when we're taking a cosine of 90 here, that's going to be at its maximum of 1, which is why the torque is at a maximum. So the correct answer choice here would be C, 90 degrees. Number 28, we're told that the solid conducting sphere of radius r shown above has a charge of plus q distributed uniformly on its surface. The potential at the center of the solid of the sphere is, well, if it's a conductor, that means that its charge is going to be out here on the surface, and also that there's basically no change here in voltage as we're going across the conductor. Again, this is a very important property of conductors, that the voltage change is 0 and the electric field is 0 as well. Okay, and so that means that really the voltage that we need to be thinking about, which is with respect to out towards infinity, is going to be caused by the electric field that's right here. But really what I can just say is that we can treat this as a point charge because it's spherically symmetric. And we can then just use this formula here from your formula sheet, um, like so. So this is just the charge, right? And this here is the distance out to the surface of the sphere. And so that means that it takes a voltage of, well, that to get from infinity to here, and then the change in voltage is going to be 0 going inside the sphere because it's a conductor, right? So that is to say that it's going to be the reason it's not going to be negative, if you want to think about it, is because it's a positive charge distribution, which means that we'd be going against the electric field, and so that must mean we would be increasing the voltage. Number 29, we're told that a circuit consists of a resistor R with an inductor L and an open switch S connected in series with a battery. And then we close the switch at time 0. So let's just close it, and now we have our circuit here. And we're asked if the current in the circuit I at time t, I should say, what energy is stored in the circuit in addition to that stored in the battery? So in addition to that stored in the battery, is basically just saying, well, ignore the battery because technically, yeah, it's storing energy. And so now we're just thinking about this, and really the energy storage is going to be happening in the inductor. It does that by creating a magnetic field, and that's how it stores its energy. And this is actually straight from your formula sheet, which is going to be that the energy stored by an inductor is going to be L 1/2 of Li squared, and really that's just it. It's going to be C right here. The reason you don't have to, well, the reason it's not going to be any of these other answers is, well, first of all, we're pretty sure about this, right? This is the energy stored in an inductor that's going to be included. So we can already eliminate any answer that doesn't include it. And then we are left here with E, which also adds I squared times R, but this here is a power, right? This is a unit. This is a wattage, right? And which means we're basically adding units that don't actually line up, which is an energy, and we're adding a power, which is a rate of energy with respect to time. So this cannot be the answer either, and so the only one that makes sense is C. Number 30, we're still working with the same circuit from before, and now we're asked which of the following quantities could be represented as a function of time by the graph shown above. And I think what we should maybe do here is imagine that we have here time is equal to 0, time is equal to infinity, and we're going to create a table here for the values that are listed, which is potential difference across the resistor, potential difference across the inductor, and current in the circuit. Okay, uh, and so if we think about it, initially the resistor is going to have, at time 0, is going to have a voltage of 0 because there will be no current passing through it, because originally the circuit was, the switch was open, no current was flowing through it. When we close it at times equal to 0, the inductor is going to fully resist all the all the current that it can, which is to say that the current originally is going to be 0. And so that means that at time 0, also the voltage across L is going to be the EMF here that I drew for the battery. Um, and then as we go off towards infinity, the voltage across the inductor slowly goes down to 0. The voltage across the resistor will end up going to infinity, or not to infinity, but to the EMF, and the current here will just depend, I guess, on the resistance of the resistor. So that is to say that we have here a graph where something is definitely exponentially increasing. Which means it's going from 0 to some positive value, and that's its asymptote. And so that seems to be like it's the potential difference across the resistor and the current in the circuit, and not the potential difference across the inductor. So the answer is going to be C, 1 and 3. Number 31 is still dealing with the same circuit from before, but now we're told that a change in the current when the switch is closed is determined by the inductive time constant tau here. If the inductance is doubled and the resistance is halved, the new inductive time constant equals, well, unfortunately, this is just something that you kind of have to memorize unless you're willing to do kind of a long derivation for this in your multiple choice section, which I don't recommend doing. But uh, the formula for a time constant of a RL circuit, so this is a RL circuit because we have a resistor and an inductor, is going to be given by this formula here. Okay. Keep in mind for an RC circuit with a resistor and capacitor, the time constant was given by RC. Now it's given by L over R. And so if we are to double the resistance, or sorry, we're doubling the inductance and we're having the resistance, then the new time constant will be 4 times what it was originally, like so. And so the answer here is E. Number 32, a capacitor of capacitance C1 is charged and then connected to another initially uncharged capacitor of capacitance C2, which is 2 times of C1, as shown above, with the switch S in the open position. When S is closed and the system comes to equilibrium, which of the following is true of the charges on the capacitors and the potential differences across them? So we're given here a peculiar circuit that we're not used to seeing, and we might be thinking, are these capacitors in series or are they in parallel? It's easier to think of them as in parallel because if you use Kirchhoff's rules, the voltage across that capacitor must equal the voltage across this one here, okay? So we can already eliminate here D and A. Again, this is just using Kirchhoff's rules. Those two voltages must be the same. And now we're left thinking about the Qs. Well, we can think about the capacitance, which relates the Q with the voltage, the charge with the voltage, that is. And so for C1, we have here basically this right here, and let's just call this Q1, and then for C2, which is really just 2 times C1, then we have this charge right here. Okay, and this Q2 we want to figure out. Well, solving for Q2, I guess, we want to basically get something that looks like this, while here Q1 is equal to C1 times V, which is to say that Q2 is going to be equal to 2 times Q1, and so Q1 is equal to 1/2 of Q2, like so. And so the correct answer here is B. Number 33, we're told that an air gap capacitor originally has capacitance C, and if a thin sheet of metal is placed halfway between the plates of the capacitor without touching either plate as shown above, the effective capacitance will be. Well, let's first imagine that there's a positive charge and negative charge here, and this is just to demonstrate that by placing this metal sheet, which is a conductor, the charges will move accordingly and basically create a capacitor in between these capacitors, which is to say it becomes two capacitors in series, okay? And so while originally there was a distance d here, now we can call this distance d divided by 2, and same thing for that one here. And so let's think about what's the capacitance of each tiny capacitor that we just made, and they're going to be the same thing, right? But we can use here this formula here, and the area really does not change, but the distance does. It's divided by 2, which really means that the new capacitance is going to be 2 times what it was originally. But then we have two capacitors that are in series, and so we use the formula that the equivalent capacitance will be given by 1 over the two capacitors that we have here in series, which is to say the new equivalent capacitance will end up just equaling C again, and so the answer here is C. Number 34, we're told that the figure above shows the paths of 5 particles as they pass through the region inside the box that contains a uniform magnetic field B directed out of the page. Which particle has a positive charge? Well, let's imagine the motion that a positive charge with a magnetic field that's moving out of the page, like so, if we have a positive charge, let's just say moving here, it will be feeling a force that's going to be downward in this scenario here, which is to say that its motion will be clockwise, okay? So we'll have clockwise motion. And so now let's just look at each of these curves and see if it's counterclockwise or clockwise. This one is counterclockwise, B is clockwise, C is going to be counterclockwise, D is inverted, but it's still counterclockwise, and E here is a straight line, so it's really neither. And so the only answer here that's correct is B, and that's it. Number 35, the final question. We're told that a long straight wire of radius A carries a current I out of the page, uh, which is uniformly distributed over the cross-section of the wire. The value of B dot dl, the integral of that, which is the line integral of the magnetic field B around the wedge-shaped path, equals which of the following? Well, this is really just Ampere's law, and it's actually not much more complicated than that. It's a pretty straightforward question, which means we just have to figure out what is the enclosed current here. And since it's uniformly distributed, we can really just think about, well, the current for the entire circle here is going to be I, but so the current for just this wedge is going to be given by whatever proportion of the total area it takes up, which is to say it's really just going to be theta over 2 pi. And you can think about why that makes sense. This really is just like geometry A-level stuff, which is to say that the overall uh, well, this part here of the equation, which is going to be equal to this, is going to be uh, just this, and oh, sorry, I should also include that we're multiplying this by I, because when we put 2 pi, which means we're including the entire thing, then it equals to I, which makes sense. So this is the theta, and so here we have something that looks like this, and this answer here is A, and that's that. And congratulations, you've reached the end of the 2012 AP Physics C Electricity and Magnetism multiple choice exam. Go on and do also the FRQ, and then use this table here to calculate what your score would be. What I've shown here is basically assuming that you're doing equally well in the multiple choice and FRQ, which might not be true and probably isn't true, but assuming it was, this is sort of the range of multiple choice questions correct that you want to be getting to be getting each score here. So if you've gotten 21 multiple choice questions right or more, that's a pretty good sign that you're on track for getting a 5, or at least you're in the range for a 5 given this composite score. Um, but yeah, I believe this is the most recent AP exam for Physics C, Electricity and Magnetism that College Board have released, the multiple choices that is. So I don't think I'm going to make any more videos after this that are at least more recent. But I hope that you found this video very helpful. I wish you the best of luck if you're taking the exam tomorrow. And yeah, let me know in the comments if you have just any general electricity and magnetism questions, maybe about this video or just some other type of question. And also if you have any suggestions for videos that I should make. But yeah, please leave a like and subscribe for more.